Hello everyone. Welcome to this NPTEL course on Advanced Reinforced Concrete Design. Now we will start with this. Mm, we are continuing on this module 2, which is on material properties. And today, in this lecture, we are going to talk about mechanical properties of concrete, particularly focusing on the long-term properties. So in the last class, last lecture, we discussed about short-term properties, including the stress strain curve behavior and the failure mechanism of concrete in compression. Now we'll continue with uh, long-term properties of concrete. Well, after attending this lecture, the student should be able to explain the stress strain relationships of concrete as per IRC 112 guideline, which is the guideline that we use for bridges in India, and also list out what are the various mechanisms that affect long-term properties of concrete. Particularly, we are going to focus on creep and shrinkage. So the student should be able to define what is creep and what are the factors that affect creep, and also they should be able to explain the effect of creep on the structural behavior. And we have different types of shrinkage. The student should also be able to explain what is shrinkage and what are the types. And finally, we'll also briefly talk about what is the effect of temperature on the material and structural behavior. So these are the expected learning outcomes from this module. Right. So we'll continue with this IRC provision, which is Indian Road Congress 112, which gives what kind of mechanical properties that we need to consider when we are designing for road bridges. They have broadly classified the concrete types into three. The first one is an ordinary concrete, which is actually made by nominal mixed proportion by weight of its main ingredients. So the last lecture we talked about what are the basic ingredients of making concrete, which include cement, cores, fine aggregates, and water. So this is done by nominal mixed proportioning. Okay. Then we also have standard concrete. That is what it is used for, mostly used for structural applications. This composes of ordinary concrete. We also add some chemical admixtures to achieve certain target values, especially for dealing with properties in the fresh condition, for example, to improve workability and so on. Generally, for these concrete, we deal with strengths in the range of M50, which is 50 megapascal. Then we have high performance concrete, which basically combines the properties of standard concrete. In addition to that, we also add a lot of mineral admixtures to provide binding characteristics. Also, some of them will act as a filler material for improving the strength and durability. Right. So, what are the mineral admixtures? Again, we talked briefly in the last lecture. They are also called as supplementary cementitious materials. They are available of different characteristics like fly ash, silica fume, metakaolin, and slag, and so on. Right. So these SCMs reduce porosity and they also modify the other properties of concrete in the fresh as well as in hardened condition. So if you see this table that is given in this IRC 112, as explained, we have three categories. Ordinary concrete, which is only M15, M20. And for standard concrete, the concrete strength ranges from 15 megapascal to 50 megapascal. And if you go back and look at IS 456 also, it allows design provisions only up to 55 megapascal. So here in bridges, usually we also use a lot of pre-stressing. So when you use pre-stressing, always if you use high strength material, it is more beneficial. So for bridge applications, again, we go for long span structures. So their use of high strength concrete and high strength steel will be advantageous. So that is why the IRC code allows for high performance concrete starting from M30 to as high as M90. And these are the characteristics. The number indicates M90 means 90 indicates 90 megapascal of characteristic strength. These are the ways different types of concrete and designations are given in IRC 112. Now, this table, which gives the main mechanical properties associated with different classes of concrete, as you can see, The strength class starts from M15 and it goes to as high as M90. In the rows, we have different properties that have been listed. For example, FCK, which is given here, which we discussed about. Then there is a, so FCK, as you remember, it is basically 5 percentage character fractal strength. That means only 5 samples are expected to 5% of samples are expected to fail below that value, right? So we talked about what is characteristic strength in the last lecture. So if you have characteristic strength, the code is also specifying what should be your minimum the mean compressive strength, which is denoted here as FCM. FCM is your minimum or mean compressive strength. So you can see here the mean compressive strength starting from for M15 it should be as from starting from 25, and for M90 it should be higher. So the mean compressive strength should be higher than your characteristic strength, and we have seen from normal distribution the code uses FCM will be actually FCK plus 1.65 multiplied by the standard deviation, and usually the standard deviation values are specified by the code. So these are the mean strength that are specified by the IRC 112. And the next we also have FCTM. FCTM is nothing but the strength of concrete in tension, that is mean strength. M stands for mean, that means the average value. The mean tensile strength for different grades of concrete is also good. As you strength of the concrete is increasing, of course your tensile strength is also expected to be increasing because tensile strength are usually expressed in terms of square root of FCK. As you get higher and higher, use higher and higher grades of concrete, your tensile strength is also expected to go. We also have other values like 5 percentile characteristic strength, and then you have 95 percentile also. For some calculations we use at 95 percentile values also. That's why it is expected to be higher value. For example, for 5 percentile it's lower value, for 95 percentage it is higher. Okay, so for some calculations for bridge applications we use this 95 value, so 95 percentage values. So that is why the code is giving you some values depending upon the grade of concrete. Then the modulus of elasticity, again it is, we have seen in the last class, as the grade of concrete increases, elastic modulus also increases, right? And also we saw that the peak strain corresponding to that concrete also increases with increase in compressive strength, and the ultimate strain at failure, however, it is going to reduce with increasing compressive strength. So we talked about that in the last lecture. And these are also the strain values are given. Again, you have 3 values that are specified: epsilon C1, epsilon C2, and then we have epsilon C3. 3 values which are part of the design curves have been listed here, and you also have a symbol 0 by 00. That means you have to divide these values by 1000. So for example, if I'm looking at for M30 concrete, epsilon C1 corresponds to peak strain corresponding to peak compressive strength. That value is listed as 2, but 2 divided by 1000 is what the value that we have to take. So that's going to be 0.002. As you can see here, as the strength of the concrete is increased, okay, again your epsilon C1 is also increasing, like what we have seen in the previous lecture. And we also have epsilon C3, which is your ultimate strain. Again, you can see that what is happening is with the increase in grade of concrete, right? What you see here is epsilon C3 actually reduces. That is what we saw in the last lecture as well. So these are the values that are specified by IRC 112. Right. So if you go back, we have used this Hognestad formula. Instead of cylinder compressive strength F prime C, we use 0.447 FCKN as per the IS 456. Here IRC 112 also uses uh, uh, a nonlinear equation, the n value, which is the exponent, to define the shape of this parabolic curve. It depends upon the grade of concrete that you are dealing with. Just like what we have seen in your Thorenfeld's model, which we discussed in the last lecture, it accounts for how this curve is changing in the linear portion. So FCD is your design concrete strength. We will talk about that. And for any value of epsilon C that is specified in this equation, I can find out sigma C, which is the stress, as a function of your design compressive strength and epsilon C2. Now you can ask me, what is epsilon C2? Epsilon C2 is nothing but your strain corresponding to this peak value. Okay, that is also given by the code. In fact, the last thing I said, in fact, epsilon C2 is the one, the code specified value. These are epsilon C1 is a peak strain, which you actually observe, but the code is trying to simplify it. And so the epsilon C2 is the strain corresponding to peak compressive strength for the design purposes. Okay, which is not the epsilon C1, is actually epsilon C2. So that is what we are seeing here. And if you recall, even the IS 456 for concrete epsilon C2 is actually 0.002. This is what it is suggested by IRC code also for grades up to 60 megapascal. So this is exactly same thing we have seen in IS 456 provisions also, right? Uh, so if you see here, the red color is your characteristic stress strain curve, and we don't use the characteristic curves, but what we use a design stress strain curve. And if you recall what we have discussed in the last class, so how do we get the FCD? FCD is arrived by dividing the characteristic strength first by partial safety factor for concrete, which is 1.5 as per IS 456. IRC 112 gives you two values, 1.5 for basic and seismic combination. But however, when you're dealing only with accidental combination, right, which are very temporary in nature, then you can reduce this factor safety by material safety factor by actually 1.2. Okay, so that's what we are using, 1.2. Right. So again, what is this alpha? If you recollect, alpha, there are two things that are considered. We have seen in the last lecture. There is one factor which is 0.8, that is basically used to convert the cube strength to cylinder strength, which is the actual material property. In addition to that, we also multiply by one more factor, 0.85, which considers the size of it. So 0.8 multiplied by 0.85 works out to be 0.67. So that is what it is suggested by IRC 112 also. Instead of the 2, here, as per IS 456, this n is going to be 2. But here, however, this exponent value, if you go to this table, it is basically going to slightly reduce. For low strength concrete, it is exactly same as what is given in the IS 456. However, as you go higher and higher in strength, this n value, the exponent value, is going to reduce. Okay. Just like we had in Thorenfeld's model, the n factor that accounts for that the nonlinearity of the curve. So here also the exponent takes into account this. So this is the way the design stress strain curve is specified in IRC 112. Okay. So one thing to note here is you should different codes will specify different stress strain curves. The fundamental essence is we should be able to estimate the capacities in a conservative sense, but you have to keep in mind tomorrow these curves can also change. The proposed curves, if more and more data is available, more and more different types of concretes are being developed, so your design curves will change depending upon what type of concrete that you are going to use. Okay, for example, for fiber reinforced concrete, this type of stress strain curve may not be applicable, so you have to test and you have to develop your own stress strain curve, so that you have to keep it in mind. Got it. So, see, when you do the calculation, sometimes this integrating this stress strain curve for calculating the compression force becomes difficult. So, IRC 112 also specifies some simplified bilinear stress strain curve, like what it is shown here. See, for example, that parabolic and straight portion can be actually idealized as a bilinear curve, like what we have here seen here. It goes to till epsilon C3, and then it remains constant till epsilon Cu3. Okay, so this is the way that we have done. Similarly, we can also use equivalent stress blocks such as rectangular or bilinear curve for design purposes if you are able to prove that such stress sustained curves are able to predict the capacities in a conservative sense. That's what the it said. Other simplified stress strain curve relationship may be used if they're equivalent to or more conservative than the ones that are specified. Okay, either you can use the code specified one, or you can actually idealize this a nonlinear and straight curve as a bilinear curve that is there. So these values are suggested in your the table that we talked about. So this is actually it should be epsilon. Actually, it should be epsilon C2. So if you go back here, so this is what we have. Sorry. So this is epsilon C3. That's correct. So if you see here, slightly less values used in the bilinear equation, and epsilon Cu3 is slightly higher value specified because they are simplifying the stress strain curve. So you see here epsilon C3 is correct. Epsilon Cu3 is your final failure strain. So if you go back and you can see this is your strain corresponding to peak in the bilinear stress strain curve. Epsilon Cu3 is your ultimate strain. So again, if you go back, epsilon C3 is kept as 1.8, which is slightly lesser than what we use, which is a 2, usually epsilon C2. And epsilon Cu3 is instead of 4, again, we use uh, uh, slightly a lower value. Okay. So again, this epsilon C3 is also reducing as the strength of the concrete is increasing. All right. So these are some approximations. Okay. So again, for static and quasi-static loads which are acting for short duration, the secant elastic modulus that can be basically the elastic modulus ECM, which is basically by finding out by drawing a slope of the line connecting origin to the sustain diagram to 0.33 FCM. So what is FCM? Again, it is the mean compressive strength. So we can calculate like this, or you can also use this ECM value that are specified in this table 6.5. But one thing is EC, the elastic modulus is again, it is proportional to square root of your compressive strength. Okay. So that's what if you see here, these values are given here, ECM is given here. As the strength of the grade is increasing, again elastic model is also going to increase. Okay, but it is going to follow square root of FCK. Okay. So which we have seen it in the previous lecture also. Right. So this is the way we calculate your elastic modulus. Now again for Poisson's ratio for concrete usually it is taken as 0.2, and after it cracks it is taken as 0. Now, when you're doing analysis for impacted shock loading, we have seen again in the last lecture the effect of strain rate. If you apply a higher strain rate, your strength increases and elastic modulus also increases. That we have seen it in the last lecture. So your material properties has to be amplified. So we have to use not the static modulus of elasticity, but we have to use dynamic modulus of elasticity, which can be taken as 1.25 times your ECM. This is what's specified in your IRC 112. Okay. Again, for calculating the stresses from seasonal temperature variations, you can take half of ECM for accounting for temperature induced stresses, which are also modified by creep effect. As we will discuss about the creep effect, the effect of creep is basically it is going to soften the material. So the elastic modulus will reduce. So if you have to include these effects, the code is saying that you take half the ECM that is specified for your static and quasi-static loads that we have discussed previously. Correct. So now let's briefly talk about how the concrete properties are going to change in long term. Okay. All the mechanical properties that we estimate, we always talk about short term properties. However, the concrete undergoes some changes in long term. So that we need to understand clear. So there are three phenomena that we actually need to account for. One is the creep effect. Okay. So creep is basically defined as increase in strain and constant stress. Okay. So that implications of the creep we will talk about it. Again, concrete undergoes shrinkage. So that effect also we need to consider in our design, and temperature effects also. So what is the effect of temperature, especially when you have um, very long span elements, it can undergo due to thermal gradients, it can develop some strains and stresses which we need to account for. Now let us briefly discuss what happens when you have. So for example, I am plotting how the strain variations are going to develop in the y-axis. Okay, in the upward, the positive values are taken as contraction, in the below values are taken as negative values are taken as expansion here. So this is the time that we are doing the casting, and as the time evolves, which is represented in the x-axis, we will see how different strains are evolving over a period of time. Let's see, this is there may be some strain before the start of drying, and then as soon as you start drying, that means you have stopped curing, moist curing, and then you let it. So this is the time T naught, which is basically the start of drying. So this location, so this is the point where we talk about. Yeah, so this is the point time at which we start drying. That means we stop curing. So as soon as you stop curing, basically you're going to have shrinkage develop. The shrinkage will have two components. One is autogenous shrinkage that is happening because of the chemical reaction. Uh, uh, because of the chemical reaction, the moment you add water with the cement and aggregates, it's going to form a solid block. So that whatever the shrinkage that's happening because of this is called as chemical reaction. We call them as autogenous shrinkage. In addition to that, there is also water that is unutilized in the hydration process that is going to be available at multiple levels. Okay, in the inside the calcium silicate hydrogel also gel pores will be there. So gel water will be there. Again, in the capillary pores, the water will be there. And then between the layers of CSH, also you are going to have adsorbed water that will be there. So all of them will try to escape over a period of time. So because of this drying also you will have a drying shrinkage. Now T is the time that which we start applying the load. So you will have, so this is the total component, the shrinkage, which is summation of your autogenous shrinkage and basically drying shrinkage. So drying shrinkage is here, the below value is the small value is your autogenous shrinkage. Again, the proportions of autogenous shrinkage and drying shrinkage will change depending upon what type of concrete that you're dealing with. For a normal concrete, if you go for high strength concrete, you end up providing more cementitious material. So your autogenous shrinkage values also can be higher. But I am talking for concrete strength, which are lower in the range of 40 megapascal, where autogenous shrinkage is usually much lower than that of drying shrinkage. Then the moment we start applying the load here, okay, you have initial strain. So that is what it is given here. Okay, so that is what you have it here. And then the strain increases. Okay, in addition to your autogenous shrinkage and drying shrinkage, you also have strain induced by the load. Then the load remains constant, but we know that over a period of time, then you are going to have basically. So this is the time that actually we are applying the load. So the strain is increasing, right? However, it doesn't remain constant. Now under constant stress, the strain is also going to increase. This is what we call it as a first component. Again, creep strains will have two components. One is a basic creep, another one is the drying creep. So you will have basic creep. The strain will keep increasing. In addition to that, you also have drying creep that is going to keep increasing. So that increase is going to be very high at the initial time, and then it is going to remain constant. Okay, we'll talk about what is basic creep and drying creep. So basic creep is when you when if you measure the strains in a sealed condition, whatever the strain that is developed due to creep, where you prevent the escape of moisture outside, that creep you define that as a grain, the basic creep. But most of the time, your concrete will be not sealed; it will undergo some evaporation loss, and then there will be escape of moisture. So you will have creep from basic creep as well as drain creep. So this is your total strain from creep. Okay, so if you look at any point of time t, you are going to have strain from shrinkage. Okay, the shrinkage will have two components, autogenous shrinkage and drying shrinkage. You have load induced strains, then the load remains constant, then you have creep induced strain. Now here the creep induced strain can be become much larger than your load induced strain as well. So it depends upon what age you are loading and what is the stress level that you are loading and so on. So this is where it actually the strain evolves over a period of time. Correct. So this is basically your stress induced strain, which includes only the initial strain and creep, which are induced by the stresses. However, the shrinkage strains are not stress induced. It is happening because of the shrinkage, right? So, but you have to add all the strains, then only you get your total strain. So, the total strain includes strain from shrinkage, strain from the load, and then strain due to creep. Now, so why this is important is especially for pre-stressing application. Uh, we stretch the pre-stressing steel, right? Imagine this pre-stressing steel like a rubber band. You stretch it and then you pour concrete and you transfer the pre-stress to concrete. Uh, but the stress in the steel will keep reducing over a period of time. So that is what it is shown in this figure here. So for example, when you jack this pre-stressing cable, so this is the stress that you will lock. And if you are doing a post-tensioning operation, pre-stressing you have two types, pre-tensioning and post-tensioning. In post-tensioning, you will have loss that is happening. That means the stress that I'm locking in this pre-stressing steel will slightly reduce because of seating loss that is happening in the anchorage. Okay, but then what will happen is over a period of time you also have losses that is happening from the relaxation and temperature loss. But then when you transfer the stress to the concrete, you will have also the concrete is undergoing deformation. So because of the deformation, there will be small reduction in strain that you're locking in the pre-stressing steel. Also, there will be that loss that is called as elastic shortening. But then again, this because of this long-term effects like creep and relaxation, the stress will slowly start degrading. Then again, what happens? You start putting your, let's say for bridge application when you're talking about, if you apply let's say cast bridge decks and you're looking at what is a stress variations in a pre-stressing girth, for example. So because of that, again, you will have some load effect that will be there. There will be stress gain due to deck placement. Then again, it will keep reducing. We are looking at what is happening for the pre-stressing cable stress levels at the level of tension side. Okay, so again you will have now that is the reason why there is a stress gain due to deck placement is because the pre-stress is going to the because the self weight of the deck, what is going to happen is at the bottom location now you are going to develop some tension, so you are relieving some stress. So that is why the stress is slightly, you are going to put more tension on the bottom, so that is why the stress is slightly increasing because of the self weight of the deck. Again, over a period of time, when you start applying the superimposed dead load, again there is a small increase in your stress depending upon how much is your superimposed dead load. Again, you look at it for a girder. Now, what we are really looking at is usually, let's say, assume that it is simply supported. Now, what we are really looking at is we are looking at, let's say, we are looking at a parabolic girder, okay, and it is subjected to, let's say, uniformly distributed load. So you know that the stress because of this self weight or the superimposed loads, you're going to have basically bending moment is going to be like this. Okay, so your stresses are going to be compression at the top and tension at the bottom. So this is compression and this is tension. Okay, so we are, let's say we are looking at this location. Okay, that's why because of this tension that is developed, you have small increase in stress. And again, when you have additional superimposed dead load that is coming, again the stress is increasing. However, there is a gradual reduction that is happening because of creep, shrinkage, and relaxation. Okay. Now again, there may be slight increase in your stress gain due to live load. So why we are talking about this is we have to consider what is the effect of creep, shrinkage, and relaxation to accurately estimate what is the level of stress that you have it on your pre-stressing cable. So that is why it is important for us to understand what is the effect of creep, shrinkage, and relaxation, especially when you're dealing with pre-stress system. However, for even regular RC systems, especially in columns and long span elements, your effect of creep will lead to more deflections, especially in beams and slabs. And the columns also you can have additional stress effects that we will discuss in the due course.